In algebra, we don't need to write the multiplication sign in general, so 4 multiplied by a is written 4a. b multiplied by minus 10 is written minus 10b. We write division using the fraction line. A divided by 3 is written a over 3. b divided by 2, then minus 7, is written b over 2 minus 7. We use powers for repeated multiplication. For example, a times a is written a cubed. Like terms have the same letters to the same powers. They can be simplified by adding or subtracting the coefficients. For example, 4x plus 3x makes 4, 7x's. Do not mix the terms with x and the terms without x. They are not like terms. We only collect 5x minus 2x as 3x. We leave plus 3 alone. Same again. 6xy plus 2xy makes 4, 8xy. 3x minus 7x equals negative 4x. Do not simplify any further, please. In this example, we have a quadratic, a linear, and a constant term. Last example cannot be simplified any further. Students tend to mix adding like terms and multiplying terms. Two terms that are not like terms can still be multiplied. Look at this example. A cubed times a squared is a to the power of 5. We can perfectly multiply terms with different powers by adding the exponents. The reason behind is clear if you take your time to write what a cubed and a squared mean. We end up with a total of 5a's multiplied together, a to the 5. To divide powers, we subtract the exponents. Why? Well, very simple. How many a's go into a? 1, so these 3 a's cancel each other out. We are left with 2 a's at the top. That is a squared. Raising a power to an exponent, we multiply the exponents. Let's say that you have a cubed squared. That means multiply a by itself, a. That gives you 2 lots of 3a's, doesn't it? That is 6a's multiplied together, or a to the 6. When taking the square root of a power, half the power. For example, a to the power of 8 can be split into a to the 4 times a to the 4. We take the square root and end up with a to the 4. Brackets usually indicate that the expression inside the bracket needs evaluating first. For example, if x equals 5 and y equals 2, to find the area of the garden A, we evaluate x squared plus 3xy first, and then we multiply the answer by 2. 5 squared is 25, and 3 times 5 times 2 is 30. So, double 55 is 110, the area of the garden. However, often in algebra, we need to write an expression without the brackets. This is because we don't know the value of a, so we cannot add a plus 2. In this case, we remove brackets. Each term inside the bracket is multiplied by the term outside. 3 times a is 3a, plus 3 times 2 is 6. Removing brackets is called expanding brackets. When expanding a bracket, each term inside the bracket is multiplied by the term outside. 2 times x is written 2x, 2 times 7 is 14. Minus 4 times x is minus 4x, but minus 4 times minus 3 is plus 12. Be careful, multiply both the sign and the number. Pay attention to the bracket, only the number 2 must be multiplied by the terms inside. 4x must be left alone, and of course then simplify as much as you can. Same here, you must multiply only minus 5 by the bracket and simplify at the end. Pay attention to this new example. We have 2 brackets, you see? That means that not only 2 needs to be multiplied, but also x. Each term in the first bracket is multiplied by each term in the second. X times x, x squared, x times 3, 3x, 2 times x, 2x, 2 times 3, 6. Collecting like terms, x squared plus 5x plus 6. Let's try a second example. X times x, x squared, x times minus 5, minus 5x, 4x, and 4 times negative 5, negative 20. Collecting like terms, x squared minus x minus 20. A bit of a challenge. The sides of a rectangle are 2x plus 3 and x minus 2. Give an expression for the area of the rectangle in the form ax squared plus bx plus c. Expanding brackets, 2x times x is 2x squared, 2x times minus 2 is negative 4x, and the rest is simple. A is 2, b is minus 1, and c is minus 6. Factorizing is the reverse process of expanding. For example, 2a plus 2b comes from multiplying 2 times a plus b. Let's fill the gaps together. In the second expression, 3 is a common factor. In the third expression, take care of the sign between them. It is negative. In the fourth example, I can see that 2 is a common factor. How many times does it go into 6b? 3b times. That's right. You only need writing 3 because 2 times 3 is already 6. Last but not least, we write 4d in the empty space. Sometimes the number 1 is needed inside the bracket. For example, if 2 is a common factor, we need 4c plus 1 inside the bracket. 2 times 4c is 8c, and 2 times 1 is 2. If 4 is a common factor, we need 2d plus 1 inside the bracket. Common factor 8 and 2e plus 1 inside the bracket. Pay attention to the minus between, and pay attention to the order of the expression inside the bracket. Sometimes a letter is a common factor. For example, ax plus ay has a common letter. To fill the gap, we need ay. B is a common factor, m plus n inside. A is a common factor, b minus m inside. Y is a common factor, 9x minus 5 inside. X is a common factor, 4 minus 3y inside. Just because expressions do not seem to have anything in common doesn't mean they don't. The most common mistake I have seen students making here is to split it into 2 fractions. Please, please, please avoid this. Instead, we factorize each expression and hopefully they will have a common factor. Voila! Cancel x plus 5 down. The answer is 3 over 2. Algebraic fractions are fractions with letters. They follow the same rules as ordinary fractions. So to simplify them, you divide by a common number, don't you? We do the same to simplify algebraic fractions. We cancel 2's down. 1x over 4y or x over 4y. To simplify this second algebraic fraction, you divide by the common letter x. A half is the answer. In this third example, we cancel 3's down. We cancel x down too, and the answer is 1 over 5y. In this other example, there is no need to expand. This is because 2 at the top and 4 at the bottom have a common factor. Dividing both sides by the common factor 2 is much easier. No need to expand neither. Dividing both sides by x plus 2, we end up with x over 3. Same again, dividing both sides leads to x minus 7 over x minus 4. When multiplying fractions, we multiply the numerators together. We multiply the denominators together, and then we fully simplify. But I think that is a bit of a waste of time. Since we are going to have to simplify anyway, why not do this from the beginning? So the way I do it is by simplifying numbers and simplifying letters separately. The only y at the top cancels the only y at the bottom. The x at the top cancels one of the x's at the bottom. 4 goes into 8 2 times. 3 goes into 9 3 times. 2 times 3 divided by x is written 6 over x. When dividing fractions, we multiply the first fraction by the reciprocal of the second fraction. The only y at the top cancels the only y at the bottom. The x at the bottom cancels one of the x's at the top. 6x times 2 is 12x with 1 at the bottom, which we don't need to write. To finish this video, I'm going to prove our first identity. We divide by a fraction by multiplying it by its reciprocal. 4 cancel each other out. X squared leaves 1x at the top. Y cubed leaves 1y at the top. 5xy is the simplified version of our algebraic fraction. We can add fractions by making sure that they have the same denominator. So what do? We multiply the first, top and bottom, by 3, and the second, top and bottom, by 5. 3x plus 5x makes for 8x, and we leave the denominator as it is. Again, we multiply the first top and bottom by 4, and the second, top and bottom, by 5. 12x minus 5x makes for 7x, and we leave the denominator as it is. And again, we multiply the first by y and the second by x. 2y plus 3x cannot be simplified any further, and we leave the denominator xy. Again, we multiply the first by 3b and the second one by 2a. 3b plus 10a cannot be simplified any further, and we leave the denominator 12ab. We multiply the first by 4 and the second by 5. 4x plus 4 plus 5x plus 10 is simplified to 9x plus 14, and we leave the denominator 20. In this example, we treat x plus 2 as a fraction out of 1. We multiply only the first fraction by 5, and we simplify, leaving the denominator as 5. The two short sides of a right angle triangle are 3x over 8 and x over 2. Using Pythagoras, find the length of the hypotenuse. To find the hypotenuse, we take the square root of the sum of the squares. The square of 3x over 8 is 9x squared over 64, and the square of x over 2 is x squared over 4. Multiplying top and bottom of the second fraction by 16, we can easily add the fractions. The square root of 25x squared over 64 is 5x over 8, the length of our hypotenuse. We are nearly halfway through our algebra foundation. If you are using this in your calculus classroom, I made it plug and play for you. Click the link below to find these lessons hosted individually, each with its own corresponding PDF to practice. It's the fastest way to get your students ready for the calculus. Now, let's look at equations. Let's use the balance method to solve the equation. I have two boxes, each of the same weight, x. That must balance exactly 30 kg on the right-hand side. Since they are identical, each must weigh 15 kg. What have I done? I have halved 30. Let's use the balance method to solve this second equation. I have one box and add 5 kg on top of it. That must balance exactly 17 kg on the right-hand side. So I could remove 5 kg from both sides. That leaves us with x equals 12 kg. Let's use the balance method to solve this third equation. I have two boxes, each of the same weight, x, and add 5 kg on top of it. That must balance exactly 17 kg on the right-hand side. So I could remove 5 kg from both, and that leaves us with two boxes of x kg each equals 12 kg. Each box must weigh 6 kg. From now onwards, I'm going to use the balance method, but picture the balance in my head. I'm going to do the same operation to both sides until we manage to leave x by itself. For example, I subtract 8 from both sides of the equation, x equals 20. In this equation, I subtract 10 from both sides. x equals -5. In this third equation, we divide both sides by 4. X equals 11/4. X over 3 means x divided by 3, so I must multiply by 3 both sides. Minus 2 times 3 is -6. We must add 12 first and then divide by 5. I add 12 because I need to get rid of -12, and for that I need to add the opposite number. If 5x equals 32, 1x must be 32/5 or 6.4. Equations with like terms require the x terms to be collected to one side and the numbers to the other side. For example, this equation has x in both sides, so we collect the letters to the left. 4x minus x equals 3x, and we collect the numbers to the right. 14 minus 2 equals 12. Dividing both sides by 3, we obtain x equals 4. This other equation has x in both sides, so we collect the x's to the left. 8x minus x equals 7x, and we collect numbers to the right. -5 minus 10 equals -15. Dividing both sides by 7, we obtain x equals -15/7. This third equation has x on the right hand side only. However, I like positive amounts of x, so I'm going to collect -4x to the left as positive 4x. We collect the numbers to the right. 25 minus 12 minus 2 equals 11. X equals 11/4. Kelly, the maths teacher, gives her class some clues. Let's calculate Kelly's age. We write an equation. X divided by 2 plus 2x equals 75. Collecting 0.5x plus 2x is 2.5x. That equals 75. So x equals 75 divided by 2.5. Kelly, the maths teacher, is 30 years old. The area of a circle is linked to the radius. Make r the subject. R squared times pi equals the area. So working in reverse, we divide a by pi and we take the square root. Changing the subject of an equation means isolating a different variable. We use the methods first introduced when solving equations. For example, if we want to make x the subject of the formula y equals 6x minus 2, imagine that instead of y, we had 10. How would you solve for x? You would add 2 and divide by 6. So you do the same if you have y instead of 10. You are going to treat y as a constant and make x the subject. If you take physics, you may have seen this formula. Make s and make u the subject. Moving u squared to the left and dividing by 2a leaves s by itself. Subtracting 2as and taking the square root leaves u by itself. I have kept this video short, but the free course features the expanded walkthroughs for every topic. You will get the full-length explanations, multiple worked examples, and PDF practice sheets to help your students really nail the process. Head to the link in my bio to get access. The easiest way to deal with brackets is to eliminate them. We do so by expanding. To expand, we multiply 3 times x plus 3 times 5. We move 15 to the right hand side and are left with 3x equals 6. X must be 2. Alternatively, we could have chosen to divide both sides by 3. 21 divided by 3 is 7, and I know that x plus 5 is 7 when x equals 2. But this may not always work that well. For example, if we divide 17 by 4, we get a decimal number. I don't know you, but I prefer dealing with decimals at the end, so instead I choose to multiply by 4 and move -20 to the right hand side as +20. Finally, and inevitably, I divide by 4 to obtain x equals 9.25. In this other example, multiplying by -2 not only doubles each term but also changes its sign. Minus 2x minus 10 equals 4, so minus 2x equals 14. Dividing 14 by -2 gives us -7. In this new equation we have an added difficulty. X is in both sides of our equation, not a problem. After expanding the bracket, we move the x's to the left and the numbers to the right. X equals -7 and 2/3. We have two brackets, so we expand each separately. We collect x's to the right and numbers to the left. 10 equals x, or x equals 10. This other equation is one that tricks the students. Pay attention. The number in front of the bracket is 3, so when expanding the bracket, we only multiply 3 by x and 3 by -2. Then, and only then, we simplify by collecting like terms. 7x minus 11 equals 0, so x equals 11/7. Brackets don't always require multiplying out. In this equation, we have a numerator acting as a bracket and a division. Since we are solving an equation, we are undoing BEDMAS by following the opposite order. So we undo division first and then undo whatever is in the numerator. 10 times 3 is 30, subtracting 2 returns 28. Let's try that again. Undo division first and then undo whatever is in the numerator. Subtract 6 and divide by 2. We were able to do this easily because we only have one fraction. 3x times 5 equals 2 times 8. 15x equals 16, so x is 16/15. It doesn't have to be a pretty number. Let's try that again. 10 times x plus 3 equals 7 times 5. Expanding the bracket and moving plus 30 to the right, x equals 5/10, or 1/2. Let's try another time. 3x times 5 equals 4 times 2x plus 1. 15x equals 8x plus 4. Yes, plus 4. Don't forget to multiply 4 by each term inside the bracket, not just 2x, but also plus 1. We then solve normally. X equals 4/7. We can solve any equation with fractions using cross product as long as we have only two fractions. By moving the fraction 6/x plus 2 to the right hand side, take care to use the minus sign only once. In this case, I'm going to multiply 4 times x plus 2 and -6 times x minus 1. 10x equals -2, so x must be -0.2. This example contains two fractions and one term plus 8. We collect the fractions to the left and keep 8 on the right hand side. Now, pay attention. Since the fractions have a common denominator, x, we can simplify the numerator, 8 minus 4, and leave the same denominator. Now, if 4/x equals 8, then 4/8 must be x. That means x equals 1/2. Again, two fractions and one term, 58. Since the fractions have a common denominator 3, we can add 1/3 and 2/3 to give us 3/3 or 1. X equals 5. And once again, two fractions and one term, adding 2/5 and 3/10 leads to 7/10. Multiplying by 10 and dividing by 7, x equals -20. This new equation contains two terms on the numerator of one of the two fractions, but this shouldn't be a problem for you now. You can expand brackets, so stop the video here and solve this equation. Right, 3x plus 6/15 minus 5x/15 leads to the fraction minus 2x plus 6/15. Multiplying by 15, minusing 6, and dividing by -2 leads to x equals -57. This equation may look a bit complicated because of the way it's written, but I want you to realize that taking 1/2 of 5x plus 3 is the same than dividing 5x plus 3 over 2. Stop the video here and try solving this equation. Right. Multiplying the first fraction, top and bottom, by 2 leads to 10x plus 6 minus 4x plus 3 in the numerator. Expanding the brackets and minusing each term inside leads to 6x plus 3 over 4 equals 2x. Solving the equation returns x equals 1.5. This last equation has an added difficulty. You have 3 instead of 2 fractions. Can you think of the best way to tackle it? Well, the denominators are 4, 5, and 10, so I'm going to convert these 3 fractions into equivalent fractions with 20 as the denominator. That way I can easily simplify the numerator and leave the same denominators. 2 fractions with the same denominator are equal if their numerators are equal. So 17x plus 21 must be equal to 16x minus 4, and so x equals negative 25. Inequations are solved in exactly the same way as equations. For example, to solve x minus 4 more than 6, we solve the equation x minus 4 equals 6 and place the same symbol back. You need to know the symbols and the meaning. For example, more or equal than 5 includes 5 and any number to the right of 5 in the number line. More than 5 does not include 5, so we signal this using an empty dot. 5 is not part of the solution, but any number bigger than 5 is. Less than means numbers smaller than 5, so they are to the left of 5 on the number line. Last but not least, less or equal than 5 includes 5 and any number to the left of 5. For example, when solving 5x plus 3 more than 23, we solve the equation which has a solution x equals 4, and we replace the same symbol back. X must be greater than 4, not including 4. That is why the circle is empty and 4 is not part of the solution. As another example, to solve the inequation, we solve 3x plus 2 equals x minus 4, and we replace the same symbol back. X must be greater or equal than negative 3, including negative 3, and that is why the circle is full. Minus 3 is part of the solution. Same again, solving the equation leads to x equals negative 6. Replacing the inequation symbol back, x must be greater or equal than negative 6. That includes negative 6 as part of the solution. Sometimes it is better to collect the x's to the right hand side. This is to avoid ending up with a negative sign in front of x. Please take care of placing the correct symbol back. 6 less than x is the same that x more than 6. Any number bigger than 6 is part of the solution. Some inequations involve brackets and require some manipulating before you attempt to solve them. Stop the video here and attempt to solve it. Right. Expanding brackets, collecting like terms, and solving for x leads to x more than negative 3. To finish with, I will go over an inequation with fractions. We solve the equation using cross product. Collecting x's to the left and numbers to the right leads to 4x equals negative 15. So x must be bigger than negative 15 over 4. A quadratic equation has 2 solutions. If the product of 2 numbers is 0, either a equals 0 or b equals 0. X plus 3 times x plus 2 equals 0, either when x equals negative 3 or x equals negative 2. If the quadratic is written in expanded form, you should try factorizing. For example, the quadratic equation x squared plus 7x plus 12 equals 0 can be factorized x plus 4 times x plus 3. You can think of the terms in your quadratic equation as areas. X squared is the area of a square, x by x. 7x is the area of 7 rectangles 1 by x. 12 is the area of 12 squares 1 by 1. Notice that we arrange them to fit into a perfect rectangle. This rectangle has base x plus 4 and height x plus 3. To solve it, solve each bracket equals 0. X plus 4 is 0 when x equals negative 4. X plus 3 is 0 when x equals negative 3. These two solutions coincide with the places where our quadratic crosses the horizontal axis. Yes, a pair of simultaneous equations gives information about two unknown numbers. They need to be solved together to give the two solutions. We use substitution when one of the variables is the subject of one equation. This is because then we can easily replace this into the second equation. For example, y equals 2x plus 1 is the subject of the first equation, so I'm going to substitute it onto the second equation. Replacing y with 2x plus 1 leads to 3x equals 6, so x must be 2. Now, we replace x with 2 to find the value of y. Since y is 2 times x plus 1, 2 times 2 plus 1 equals 5. The value of y. The solution is x equals 2 and y equals 5. Let's look at some applications. A flat white costs 75 cents more than an espresso. The total cost is $8.25. Calculate the price of the espresso. Since x is the subject of the first equation, we can easily replace it into the second one. This leads to the equation y plus 0.75 plus y equals 8.25. 2y equals 7.5. So y equals 3.75. In our previous video, we solved a pair of simultaneous equations by substitution, but sometimes it's much easier to use elimination. Just by adding or subtracting, we can eliminate either x or y. For example, the sum of two numbers is 10 and their difference is 6. This is your typical example that can be solved by simply adding both equations. The y's cancel each other out and we are left with 2x equals 16. Since x equals 8, y must be 2. But when the y's have the same sign, well, adding won't help. We need subtracting, and we can. If the left-hand side equals the right-hand side, the difference of the left-hand sides will still equal the difference of the right-hand sides. Subtracting 3x minus x leads to 2x. Subtracting 17 minus 11 leads to 6. X must be 3. Since x plus y equals 11 and x is 3, well, y must be 8. That completes our deep dive into the algebra foundations for calculus. If these lessons helped you or your students today, please hit the like button and subscribe. It is the best way to help me reach more educators. Don't forget that you can access the individual videos and PDFs to practice at my website. Use them in your classroom to save time and keep your students on track. Thanks for watching, and I'll see you in the next masterclass. Happy learning!